Okay, in this video, we're going to start looking at the group of symmetries. Now, first off, we're just going to consider functions. So let f and g be elements of the group with the binary operation star, which represents composition, so composite functions. Okay, given that f is equal to 3x and g is equal to 2x squared, we need to find f combined with g. Okay, the reason I want to talk through this is because we're looking at a binary operation here that involves composition. Okay, we actually approach things in a slightly different way, which maybe contradicts some of the other things that we do. Okay, if we're doing f combined with g, thinking back to GCSE and what you learn about composite functions there, what you actually end up doing is you do the right element first, then the left one. So linking it to the Cayley table, I know we usually would say that the element written on the left would be the one we do first. We actually do the element at the top first for composition. Okay, because if you're doing f combined with g, what you want to do is take the g at the top and substitute it into the f. Okay, so if I was finding f combined with g here, okay, this would be equal to, and we're going to take the 2x squared and we're going to sub in for x in the 3x. So we would get 3 lots of 2x squared, which comes out as 6x squared. Okay, so that's a recap of composite functions from GCSE. And this keyword composition, whenever we see this in our binary operation, you're actually going to do the element at the top of the Cayley table, the right element first, okay, and then the left element. Okay, next question's about shape. So how many lines of reflectional symmetry does a regular n-sided polygon have? So what do I mean by a regular n-sided polygon? Well, if we considered a regular 4-sided polygon, well, that would be a square. Okay, so I've got my square drawn here, and it's essentially asking how many lines of symmetry does our square have? Well, you got one here, got another one here, got another one here, and then we got another one here. Okay, so we have 4 in total, and if you tried it for a regular pentagon, we'd have 5, or for an equilateral triangle, we'd have 3. So the answer is n. Okay, nice and easy to remember. If it's a regular shape, okay, then it's just going to be equal to the number of sides. Now, the other thing we have to consider is rotational symmetry. Okay, so if we consider for the square, I'm just going to label A, B, C, and D. Now, when we talk about rotational symmetry, we're essentially asking, if I was to rotate this shape 360 degrees, how many times during this rotation will the shape look exactly the same as it is drawn on my page right now? Okay, so if you were to rotate 90 degrees, okay, the shape would look exactly how it started. Of course, we would have a shift of the labeling of the vertices, but that's not really relevant to determining rotational symmetry. Okay, and then the same thing would happen if I was to rotate a further 90 degrees. And then if I was to rotate a further 90 degrees, the same thing would happen. And then if I was to rotate a further 90 degrees again, the same shape would occur. Okay, so you'd end up with an answer of 4, okay, which is equal to the sides again. Okay, so for both of them, the answer is just going to be n, providing it's a regular shape. And we're going to mainly be considering regular shapes in this video. Right, so what's the definition of a symmetry group? Well, the symmetry group of a geometric object is the group of all transformations that map the object onto itself. Okay, and these transformations will usually include rotations and reflections, as well as the identity transformation. Okay, so let's consider the equilateral triangle, okay, because that's a regular 3-sided shape, but we're going to mainly be considering the regular ones in this video. So which transformations would an equilateral triangle be invariant under? So when we say invariant, okay, we mean it will look exactly the same. Right, so if we were to start with our reflections, okay, if I was to reflect my triangle in this line here, it would look exactly the same. If I was to reflect through this line or through this line, it would also look exactly the same. So in total, we have 3 reflections that we're going to have to consider, okay, through each of the vertices. Now for rotations, well, for a square, it was every 90 degrees. For our equilateral triangle, okay, it's going to be every 120 degrees. Essentially, it's going to be 360 divided by the number of sides, which in this case is 3. So it's going to be every 120 degrees, and we're going to get the same shape. Okay, so one transformation would be 120-degree rotation, and you could say clockwise or anti-clockwise. So I'm just going to say clockwise. Then add 120 again, you get 240. Okay, and then add 120 again, and you get 360. Now 360 is a special one because that will put the shape exactly in the position you started with, even with the vertices labeled. Okay, so essentially a 360-degree rotation actually has no impact on the shape. Okay, so our 360-degree rotation would actually be our identity transformation. Right, the binary operation will be the composition of transformation. So we got that word composition there again. So you're going to do the right element first, the one at the top of the Cayley table, then the left one, okay, when you're doing this. Right, so an equilateral triangle has 6 symmetries, including rotations and reflections, which we've already discussed. Show that the set of symmetries form a group under composition, and then we got a few follow-up questions once we have done that. Okay, so the first thing I'm going to do is I am going to write out our elements. Okay, and I'm going to sort of name them all for convenience. So I'm going to start by drawing out an equilateral triangle, and my advice is label one vertex 1, another one 2, and another one 3. Okay, and my first element is going to be my identity, okay, which we're going to call E, which is essentially do nothing. Okay, so that the equilateral triangle will just look exactly how it's written, even with the number labels on there. Now let's do our rotations. So let's call R1 a rotation by 120 degrees clockwise. And in terms of how my shape would look, so if I draw my equilateral triangle, okay, the 1 would rotate around here. Okay, so the 1 would then be there, the 2 would move on to the next vertex, and then the 3 would be at the top like that. Okay, so that would be the picture I could use to represent it. Okay, so just to be clear, the elements are the transformations written here. The picture above is just going to help us represent things and help us fill out the Cayley table. Okay, then we're going to name R2. So R2 is going to be our rotation by 240 degrees clockwise. You could also say 120 degrees anti-clockwise, that would be fine. But essentially, to get my picture representation, what I'm going to do is take my R1 picture and I'm going to rotate a further 120 degrees. So the 1 is going to move over to the left. Okay, so we're going to have the 1 there, the 2 will be at the top, and then the 3 will be down there, like that. Okay, so that would be my picture. Okay, let's now move on to our reflections. So I'm going to start by drawing my picture. And my line of reflection I'm going to do first is going to be this one. I'm going to call it A. So we'll say that S1 is equal to a reflection in A. Now, in terms of my vertex labeling, well, this line goes through the initial 1 vertex, so that's going to stay the same, but the 2 and the 3 will swap over. So I'd have 2, and then I'd have 3 like that. Now let's do S2, okay, where I'm going to pick a different line of reflection. Okay, so my next line of reflection is going to be this one here, which we will call B. Okay, so this is going to be a reflection in B. And in terms of the vertices, the 2 will stay where it is. The 3 even will stay where it is. Okay, and then the 1 and the 2 will be the ones that swap. So we'll have a 2 and then we'll have a 1. Okay, I've got one more reflection left, so S3. So draw my picture, and this time it is going to be through this line here, which we will call C. So this is equal to a reflection in C. Okay, and this time the 2 stays where it is, the 1 goes down here, and then the 3 will end up over there. Okay, so those are my elements in terms of the transformations drawn out and then some pictures to actually represent them. And now let's have a go at trying to construct this Cayley table. Okay, so we're going to have E, R1, R2, and then it's going to be S1, S2, and S3. Okay, and then we have E, and then the same sequence. Like that. Now let's fill in the easy parts first. The identity, I'm just going to make a bit of space. The identity doesn't do anything to any of the elements, so we're just going to write out the same row again. And then same for the column. Okay, so let's start working through. Let's just stick with the rotations initially. Okay, so for this element here, okay, you'll be doing R1 combined with R1. Okay, so we have a rotation by 120 degrees here, and then we're going to follow that with another rotation of 120 degrees. So that should be equivalent to a rotation by 240 degrees. So therefore, my final answer in here is going to be R2, okay, because that represents a rotation by 240 degrees. Now, if we move on to this element here, we would be doing R2 combined with R1. So if we do R1 first, that's a rotation by 120, and then we follow it with a rotation by 240, which is equivalent to a rotation by 360, which is my identity, okay, because that doesn't do anything. So we've got E in there. Now let's move over here. Okay, so this time it's going to be R1 combined with R2. So we do R2 first, which is a rotation by 240, followed by 120. So that's going to give me 360, which is going to be E again. And actually what we'll find is it doesn't matter which order you do your rotations in. Okay, they are commutative for the rotations. So that will just help you fill things out a little bit quicker. Now, next one here, we have a rotation by 240 followed by 240. So that would be equivalent to a rotation by 480 degrees. Okay, now if we subtract 360 off that, because it's larger than 360, we end up with a rotation by 120 degrees, okay, which would be R1. So I'm going to put that in there. Okay, like that. So you can see if you combine a rotation with a rotation, you will get the identity or just another rotation there. Right, so let's move on to some of our reflections next. Okay, so let's go for this element here. Okay, so that is going to be R1 combined with S1. So we're going to do S1 first. So I'm just going to draw a picture of S1 out here just to help us. Okay, so our picture for S1 was 1, 2, and 3. I am then going to rotate this picture by 120 degrees to represent R1. So this is going to become, if I rotate it 120 degrees clockwise, the 1 is going to end up down there. So we have 1, and then 3, and then 2. Now what you're going to do is compare this resulting picture to your 6 elements and figure out which one does it match with. So the one that it matches with would be S2. Okay, so therefore we would put S2 in here there. Okay, so let's move on to the next one. Let's do S1 combined with R2. So I'm going to write out, or it's R2 combined with S1, sorry, as you write it out. But you're going to do S1 first. Okay, so we got our picture of S1 already drawn above, so I'm just going to draw it in again. And this time we're going to rotate by 240 degrees. So the vertices are going to skip on 2 instead. So the 3 in the bottom right will go up to the top. Okay, and then the 1 would be down here, and then the 2 would be over. So then take this picture and compare it to what we've got. And I believe it matches with S3. So we're going to put an S3 into here, like that. Okay, so we dealt with that. So I'm just going to make a bit of space, and let's go through another combination of elements. So let's do this one here. So for this one here, it's going to be R1 combined with S2. So I'm going to start by drawing out a picture of S2. So S2 is 3, 1, 2, like that. And then we're going to rotate by 120 degrees. So all the vertices are going to move on 1. So that'll be 1, 3, 2. And then we're going to compare this picture to our elements. Okay, and we've ended up with S3. Now we can use our Latin square property because we're going to show this as a group. Okay, so to speed things up, I believe from this row here, S1 is what's missing. Okay, so we can get that in there. Now let's do this element. So that's going to be R2 combined with S2. Okay, so we got our picture of S2 here. And then we are going to rotate by 240 degrees. So the vertices are going to move on 2. So 1 is at the top, 2 is over here, and 3 is there. Okay, so we've ended up with this picture here. And if we compare to our elements, that would be S1. And then all that is missing from that row would be S2. Okay, so I can fill that in there. Right, so let's now rub this out and let's do some reflections combined with some reflections, as that's probably the one thing we haven't looked at yet. Okay, so let's do this element here. Okay, so that is S1 combined with S1. So I'm going to start by drawing out S1, which is 1, 2, 3. Okay, then this represents this other S1, so we're then going to reflect in A. So I'm going to draw A on here. Okay, and we're going to reflect. So the 1 is going to stay where it is, the 3 is going to go here, and the 2 is going to go there. Then let's compare this picture to my elements. Okay, and the picture that I've ended up with here, okay, is the identity. Okay, and this makes sense because if you reflect a shape in a line, then reflect it in the shape in the same line again, okay, you're just going to end up back with what you started with. Okay, so any reflection combined with itself is going to be the identity. Okay, so I'm going to fill in E there, and fill in E there as well. Okay, so that's a useful fact. That is going to just help speed things up. Now let's do S1 combined with S2. Okay, so let's draw out the picture for S2. So S2 is 2, 3, 1. We're then going to reflect in S1. So S1 was this line here. Okay, so 2 stays where it is, and then the 1 and the 3 will swap. And then let's compare this picture to my elements. So we got 2 at the top, then 1 and 3. So we're going to get R2 as my result here. Okay, then let's use our Latin square property. That should have been R2. Okay, so you get R1 at the very bottom there, so that's filled out. Now let's have a go at this one here. Okay, so let's just make a bit of space. Okay, so for this one here, we'd have S1 combined with S3. Okay, so let's draw out the picture of S3, which would be the following. So we got 3, 1, 2, and then we're going to reflect in S1. Okay, and S1 is this line here. So the 3 stays where it is, the 2 and the 1 swap. Okay, then let's compare to my pictures, and it's going to be R1. Okay, so hopefully what you're noticing as well is if we combine a reflection with a different reflection, we're actually ending up with a rotation each time. So this one here should be R2 using our Latin square property. And then let's continue from there. So we'll go for this one. So it's going to be S2 combined with S1. So we're going to draw S1. 1, 2, 3. And then we're going to reflect in S2. So that would be this line. So the 2 stays where it is, and then the 1 and the 3 are going to switch. Okay, so if you look at my rotations, it's going to be R1, okay, which is what comes out. And then therefore we're going to have R2 at the bottom there. Okay, so let's now move on to the final bit of our Cayley table, which is going to be reflections and rotations combined. We know when that happens, we get reflections as our final answers. So let's start with this one here. So we're going to do S1 combined with R1. Okay, so if I draw out R1 first, I would have 3, 2, 1. Then S1 is a reflection through this line here. So then 3 stays where it is, and then we get 1 and 2. So if we compare to our reflections, that is going to be S3. Then using Latin square property, this is going to be S2. Now let's do this one here, which I believe should be the last one I have to do manually. So S2 combined with R1. So we write out R1, which is already written above. And then we're going to reflect in B this time, okay, S2, which is this line here. So when that happens, the 2 stays where it is, and then the 1 and the 3 will swap. And if we compare to our reflections, I believe that is S1. So we'd have S1 here, S3 would have to go here, S2 would have to go here, and S1 would have to go there. And that would be our complete Cayley table.